Hi class! Welcome to the LEGO Bricks in Space program. It's time to get out your student worksheet. Working alongside the crew on board the International Space Station, you will find all the answers to the questions on your worksheet. Teachers, when you see the pause prompt on the screen, please pause the video to give students time to record their answers. Hold on to your seats as we launch into space.
Welcome to my on-orbit classroom. In the story, we learned that the astronauts were in need of a measuring device that would help them measure a group of space boots. To do this, we created a Trundle wheel like this. Now that you have some experience with how a Trundle wheel works, let's apply that knowledge to space. We are going to follow the scientific method and starting with asking a question. How is physical space divided up differently in orbit than on Earth? And how do we measure that? Next comes research. We already know that the Trundle wheel works on Earth, but will it work the same way in microgravity? It has a wheel that must be pushed down, but the rest of the device should work just like on Earth. We know that the Trundle wheel is calibrated, meaning that the complete one rotation of this marker is equal to 100 centimeters. Do you think the Trundle wheel will work the same as it does on Earth? And whose physical space is larger, yours or mine? Let's find out. While you mostly use a desk or table for your schoolwork for this activity, I have to use a maintenance work area or MWA. Now that we have used science to calibrate both our Trundle wheels, let's compare workspaces. In space, it is important to keep objects, especially small Lego bricks, confined to a specific area so that we don't lose them. They can float off and get stuck someplace on the ISS that could create an unsafe environment on the ISS. As you can see, items can easily float away. The MWA with containment system allows us to conduct experiments without worrying about things floating off. It does limit, however, our working area. Let's measure this MWA. The size of this MWA is 66 times 86 times 61 centimeters. The MWA measurement in inches is 26 times 34 times 24 inches. How does that compare to your workspace in your classroom? You will want to write both these measurements down on your worksheet so you can compare them to help prove your hypothesis. Now let's see how big my lab is compared to your classroom. The International Space Station US lab is 346 inches or 879 centimeters in length and 168 inches or 445 centimeters in width. How does that compare to your classroom? I'm willing to bet your classroom is much larger than mine. Again, write this down on your worksheet so you can compare them to help prove your hypothesis. While it is interesting to see the differences between our environments, it is important that we keep measurements accurate. On the ISS, accuracy is vital. Objects brought on board the ISS have to fit in within certain measurement criteria. Let's see how far we've come in our investigation of measurements in space. We asked a question, conducted research, made a hypothesis, and just conducted 2 experiments that tested our hypothesis. Now, all that's left is analyzing the data and creating a conclusion. Well, our time is about up, but before I leave, I wanted to ask you a few questions to keep your exploration of space going. Did the Trundle wheel work in space the same as it did in your classroom? How would you check this for accuracy? Hint: what were our units of measurement for each object we measured? Do you think there are objects that might measure longer or shorter in space than they do on Earth because of microgravity? What ways could you adjust your Trundle wheel? What would happen if you used a larger wheel, for instance, or added a second dial? Thank you for stopping by my on-orbit classroom. See you soon!